Greetings, and welcome to another episode of the Galaxy Report. The Galaxy Report is here as a part of the Daily Galaxy. I'm Nicole Butscher, and this week we're going to be taking it to the center of our galaxy, a place that has been intensely studied for many years, but still continues to harbor surprises for scientists, as well as breaking news stories. A snake-like structure lurking near our galaxy's supermassive black hole is one of the more intriguing discoveries. Part of the thrill of science is stumbling across a mystery that is not easy to solve, says Junhui Zhao at the Harvard Smithsonian Center for Astrophysics. While we don't have the answer yet, the path to finding it is fascinating. We have made very good progress by obtaining a new VLA, or Very Large Array, observation of the mysterious region, Zhao writes in an email to the Daily Galaxy. And we are analyzing the data to nail down the nature of this snake-like filament source. Meanwhile, based on the new data, we have found some fascinating results on a population of galactic center compact radio sources, or GCCRs. The GCCRs may mark the headstones into the stellar graveyard at the center of our galaxy. In 2016, Farhad Youssef Zadeh of Northwestern University reported the discovery of an unusual filament near the center of the Milky Way, using the NSF's Carl G. Jansky's Very Large Array. The filament is about 2.3 light-years long and curves around to point at the supermassive black hole, called Sagittarius A, located in the galactic center. Another team of astronomers has employed a pioneering technique to produce the highest quality image yet obtained by this curved object. We still have more work to do to find out the true nature of this filament. With our improved image, we can now follow this filament much closer to the galaxy's central black hole, and it is now close enough to indicate to us that it must originate there, says Mark Morse of the University of California, Los Angeles. The researchers have considered three main explanations for this filament. The first is that it is caused by high-speed particles kicked away from the supermassive black hole. A spinning black hole, coupled with gas spiraling inwards, can produce a rotating vertical tower of magnetic fields that approaches or even threads the event horizon, the point of no return for infalling matter. Within this tower, particles would speed up and produce radio emissions as they spiral around magnetic field lines and stream away from the black hole. So that's the first possibility. The second, more fantastic possibility is that the filament is a cosmic string. This is theoretical, as yet undetected objects that are long, extremely thin, and carry mass and electric currents. Theorists had predicted that cosmic strings, if they do exist, would migrate to the center of our galaxies. If the string moves close enough to the central black hole, it might be captured once a portion of the string crosses the event horizon. Assuming they do exist, reports LIGO, the network of cosmic superstrings formed in the early universe would have evolved as the universe expanded. Strings stretched, interacted, oscillated, and disintegrated. Massive computer simulations can describe this evolution from formation up to today, but they are challenging because many physical effects need to be taken into account. There is currently no observational evidence of the existence of cosmic strings, LGO adds, and the cosmic microwave background radiation evidence proves that they are not abundant. One of the most promising ways to detect these elusive objects is to search for the gravitational wave radiation they would produce. Gravitational wave emissions is the main mechanism for cosmic strings to dissipate energy. When a string in a cosmic string network crosses itself, a loop separates from the string. In spite of all our efforts, no evidence of a cosmic string signal has been found in LIGO Virgo data. As often in experimental physics, a null result doesn't mean we didn't learn anything. The final option is that the position and direction of the filament aligning with the black hole are merely coincidental superpositions, and there are no real associations between the two. This would imply it is like the dozens of other known filaments found far away from the center of the galaxy. However, such a coincidence is unlikely to happen by chance. Each of the scenarios being investigated would provide intriguing insight if proven true. For example, if the filament is caused by particles being ejected by Sagittarius A, this would reveal important information about the magnetic field in this special environment, showing that it is smooth and orderly, rather than chaotic. The second option, the cosmic string, would have provided the first evidence for a highly speculative idea, with profound implications for understanding gravity, space-time, and the universe itself. Evidence for the idea that the particles are being magnetically kicked away from the black hole would come from observing that particles further away from Sagittarius A are less energetic than those close in. A test for the cosmic string idea will capitalize on the prediction by theorists that the string should move at a high fraction of the speed of light. Follow-up observations with the Very Large Array should be able to detect the corresponding shift in position from the filament. Even if the filament is not physically tied to Sagittarius A, the bend in the shape of this filament is still unusual. The bend coincides with and could be caused by a shock wave, akin to a sonic boom, where the blast wave from an exploded star is colliding with the powerful winds blowing away from the massive stars surrounding the central black hole. We will keep hunting until we have a solid explanation for this object, says co-author Miller Goss from the National Radio Astronomy Observatory in Socorro, New Mexico. And we're aiming to next produce even better, more revealing images. We're still pursuing what this filament might be. All possible explanations except one seem to be very interesting, wrote UCLA's Mark Morris. The one explanation that is not so interesting is that of the many radio filaments seen towards the central few hundred parsecs of the galactic center, just happening to be accidentally superimposed along the line of sight in just such a way that it appears to be linked to the central supermassive black holes of our galaxy, explains Morris in an email to the Daily Galaxy. The probability of this, however, seems quite small. The more interesting hypothesis, suggests Morris, is that the energy generated by the accretion flow of the black holes onto the black holes produces highly energetic particles, or electrons, that stream out from the black hole and are trapped in a local magnetic field, just as the solar wind is trapped by the Earth's magnetic field to produce the Van Allen radiation belt. As the relativistic electrons stream along the magnetic field lines, they emit radio radiation that illuminates the magnetic field lines, also known as flux tubes, into which they are trapped, creating a linear filament of emission. A more exotic possibility, says Morris, is that the filament is a cosmic string. Continuing on the possibility that it's a cosmic string, Mark Morris adds that if they exist, cosmic strings that cross through the event horizon of a black hole can conceivably become trapped, creating an eternally wagging and radio-emitting tail to the black hole. The black hole itself is such a bright radio source that it tends to drown out the radio emissions from the portions of the filament nearest the black hole. So, although the filament gets very close to the black hole and points right at it, we can't be sure that it is yet connected, concludes Morris. Our efforts now are aimed at improving our images to see whether we can follow the radio filament much closer to the black hole's event horizon. That's it for today's galaxy report. Let me know in the comments which possibility you think is most likely. This story was published first on thedailygalaxy.com by Avi Shapur, who's a research scientist at the MIT Cavalli Institute for Astrophysics and Space Research. I'm Nicole Butscher. Make sure to like and subscribe, and I'll see you guys not next week, but the one after that. Stay well.